Okay, welcome back, everybody. So, fun fact: I have a real janky setup where I have my computer set up on top of an upside down garbage can that is on top of the podium inside the classroom. So, it's currently being like the back is kind of at an angle and it's currently being held up by a remote for the TV. So the remote started to slide away, hence the craziness at the end of that last video. All right, so let's return back to this proof to show that this thing is symmetric. So remember, we're trying to show that if A is congruent to B mod n, that B is congruent to A mod n. Or in other words, that this ordered pair A comma B, if that's in our relation, that B minus A must also be in our relation. So we've assumed that this is true here. So now we would like to be able to use the definition because we know this is true, so we can obviously say that this must be true. This implies there exists an integer k such that a minus b is equal to kn. So we know that there must exist this integer k. Now, what we're trying to work with is not going to be the same thing. We're trying to reverse these. So if we had b on this left side and the a, then that's going to switch the order. So we are looking at b minus a. Why does there exist an integer k such that b minus a is equal to kn? So indeed, now all we do is we just say, okay, what about b minus a then? So notice that b minus a, so if I flip these two, I'm just multiplying by a negative, right? If I multiply this by a negative 1, I get negative a plus b, or b minus a. So notice b minus a is equal to negative kn. So then we could say that since k is an integer, this implies that negative k is also an integer. Hence, by definition, b is congruent to a mod n. And so that concludes this proof over here, and that concludes that proof over there. So, well, I guess this one was already concluded. This one is now concluded. So the last one we have to work with is transitive. So let's take a look at transitive. So remember, when it comes to transitive, we're saying that if A is related to B and B is related to C, then A must be related to C. Or in this case, if A is congruent to B mod n and B is congruent to C mod n, is A congruent to C mod n? Or intuitively, we're saying that if A has the same remainder as B when you divide it by n, and B has the same remainder as C when you divide it by n, does A have the same remainder as C when you divide it by n? So yes, look at a bunch of examples if you'd like. You're able to convince yourself that this indeed is true. So we have a proof of this. So we could say let A, B, C be integers, n be a natural number, such that A is congruent to B mod n and B is congruent to C mod n. So again, we assume that these two are true. And then based off of these, how do we manipulate this to be able to get that A is going to be congruent to C mod n? So we'll just unpack these definitions using this over here. So what that means is that there exists some k and j in the integers such that a minus b is equal to kn and b minus c is equal to jn. So we know that there exist these integers that make both of these true. Now, if we're trying to show that a is congruent to c, then that means we're trying to get a minus c equal an integer times n. So we're trying to show that there is the existence of an integer. So why must there be an integer? Well, if we look at a minus b is equal to kn and b minus c equals jn, to be able to get a minus c, well, we could just add these two. Right? If we take a minus b plus b minus c, the b's are going to cancel and we're left with a minus c. So by adding these, we see a minus c is equal to kn plus jn, which is the same thing now as k plus j times n. So now we have shown that a minus c is equal to this, but to use the definition, we need to argue that this is an integer. So we could now say that since k and j are integers, and the integers here in z is closed under addition, we have k plus j is also an integer. Hence, A is congruent to C mod n. And that was our goal, is to have this be our statement. So indeed, this is transitive. So if we know that this congruence is a relation, and we have just shown that it is reflexive, symmetric, and transitive, what type of relation is it then? Well, remember, we said that if something has all three of these properties, that's the nicest type of relation. So congruence is a relation. It is an equivalence relation. So that is great news. This is why a whole bunch of upper level math is going to be based off of the idea of congruence. A whole bunch of modern algebra is based off of looking at congruences. There's a whole study of a number theory. So there's a whole bunch of things that you can study with numbers. Congruence plays a vital role in understanding all of the number systems that we understand. So we're going to continue to delve more into congruences, especially knowing that it is now an equivalence relation, so that allows us to do a whole bunch of really cool things with it.